Merhabalar herkese. Bugünkü webinarımıza hoş geldiniz. Öncelikle sizlere kendimi tanıtarak başlamak isterim. Ben Ekin Akın, BİAS Mühendislik'te lisanslama ve eğitim uzmanı olarak görev almaktayım. BİAS Mühendisliği kısaca tanıtmam gerekirse, BİAS makine mühendisliği disiplinleri çerçevesinde ileri mühendislik çözümleri sunan Türkiye'nin en köklü firmalarından biri olup Ar-Ge, CIA yazılımları, test ölçüm sistemleri satışı, proje analiz ve test ölçüm hizmetleri de ana çalışma alanları olmaktadır. Detaylı bilgi almak için web sitemizi ziyaret edebilir veya tüm sorularınızı info@bias.com.tr adresinden bizlere iletebilirsiniz. Softinway ve BİAS Mühendislik İşbirliği ile gerçekleştireceğimiz bugünkü webinarı uzman mühendis Ladislav Kotechenkov gerçekleştiriyor olacaktır. Webinar esnasında sormak istediğiniz tüm soruları bize chat üzerinden iletebilirsiniz. Webinar konusu ile ilgili detaylı bilgi vermek üzere mikrofonu Ahmet Bey'e devrediyorum.
Teşekkürler Ekin Hanım. Şöyle ekranımı paylaşayım. Bugünkü webinarımızın temel konusu bir boyutlu sistem modellemesi ve bu modellemeyi gerçekleştirdiğimiz Upstream'in System Simulation yazılımı. Herkese tekrar merhabalar. İsmim Ahmet Kolanoğlu. Kıdemli CFD mühendisi olarak BİAS Mühendislik firmasının ODTÜ Teknokent ofisinde çalışıyorum. Bugünkü webinarımız üzerinde ilk olarak ben Türkçe olarak kısa bir girizgah yapacağım. Sonrasında sözü Vladislav'a teslim edeceğim. Vladislav, as we discussed, I will make a short introduction and give you the floor. Bir boyutlu sistem modelleme, yapının karmaşıklığı ve üç boyutlu modellemede karşılaşabileceğimiz sorunları aşmak üzerine oluşturulan sistemlere diyoruz. Genel manada baktığımız zaman bu yansıda gördüğümüz sistemler bir boyutlu olarak modelleyebileceğimiz ve modellemenin faydalı olabileceği uygulamaları göstermektedir. Hidrolik ağlardan tutun da yağlama sistemlerine kadar geniş bir yelpazede aslında bir boyutlu sistem modellemeyi gerçekleştirebiliyorsunuz. Burada gördüğümüz gibi uçaklarda ve gemilerde geniş bir kullanım durumuna sahip hidrolik ağı görüntüleyebiliriz. Burada her bir boru içerisinde akan hidrolik sıvı ve akışkanın farklı özelliklerinde, ilerleme durumlarında, birbirine karışma gibi durumları veya da bunları kontrol eden kontrol valflerinin durumlarını 3 boyutlu bir modeliniz olmaksızın ve 3 boyutlu bir CFD analizine ihtiyaç duymaksızın bir boyutta daha hızlı ve sorunsuz bir şekilde hesaplayıp o şekilde sistemi daha hızlı bir modellemeye geçmiş oluyorsunuz. Bu sayede hem 3 boyutlu yaptığınız 3 boyutlu veya da yapacağınız 3 boyutlu analizlerin sayısını azaltmış oluyorsunuz. Hem de bütün sistemin nasıl modellenmesi gerektiğini girdi ve çıktı parametreleriyle birlikte modellemesini yapabiliyorsunuz. Veya da ısı eşanjörlerini göz önünde bulundurduğumuz zaman ısı eşanjörleri de yaygın bir 3 boyutlu CFD analizlerinde gördüğümüz bir sistem olarak karşımıza çıkıyor. Ancak sistem içerisinde yer alan çok ince yapılar sebebiyle ve termo akış durumunda incelendiğinden kaynaklı çözüm süreleri uzayabiliyor. Ve bu çözüm sürelerinin uzaması bizim tasarım tarafındaki en kritik durumumuz olan işi yetiştirme tarafında sıkıntı yaratabiliyor. Bu sebepten kaynaklı başlangıçta bir boyutta bu durumu gerçekleştirmek, ilgili yapıları kütüphaneden çekip fiziksel ve termodinamiksel özellikler girerek bu işlemi daha hızlı ve sorunsuz bir şekilde çözümüne elde edebilirsiniz. Veya da bir buzlanma önleyici sistem. Buzlanma önleyici sistemler de uçaklar için kritik bir öneme sahip bir sistem. Hem soğuk ve karlı kış günlerinde bu sistemlerin faal ve düzgün çalışması neticesinde uçağın kontrol yüzeylerinde oluşabilecek sıkıntıları gidermeyi hedefleyen bir sistem. Yine bu sistemde de 3 boyutlu bir şekilde modellemek veya da bu modeliniz neticesinde doğru şeyi tasarlayıp tasarlamadığınızı görmektense bir boyutta bunu çok daha hızlı ve kolay bir şekilde gerçekleştirilebiliyor. Peki bugünkü webinarın konusu olan Upstream sistem modellemesi ve detay konusu olan Vladislav Bey'in anlatacağı bölümde hangi yazılım kullanıyor? Upstream System Simulation dediğimiz bir yazılım. Aslında bu Upstream'e aşina olan kişilerin bildiği iki yazılımın birleştirilmesi neticesinde oluşuyor ama mantık şu şekilde işliyor. Önceki durumlarda bir Upcycle isimli aracımız vardı. Bu araç 0 boyutlu ve 1 boyutlu termodinamik çevrim analizlerini gerçekleştirebiliyordu. Upstream.net ise 1 boyutlu termo akış sistem modelleme işlemlerini gerçekleştirebiliyordu. Daha çok akış tarafındaki sistem modellemesini. Bu iki yazılımın birleşmesi neticesinde Upstream System Simulation karşımıza çıkıyor ve çok daha anlamlı, çok daha hızlı sonuçlara ilerlenebiliyor. Burada ilgili kişilere, mühendislere termodinamik döngülerin ve sıvı sistemlerinin gerçek dünyada nasıl davranacağını hem tek bir esnek ve kullanıcı dostu yazılım arayüzünde modellemek ve inceleme imkanını size sunmuş oluyor. Standartta zaten bu tip yazılımlarda hep gördüğümüz sol tarafında bir model kütüphanesi bulunuyor. Model kütüphanesini içeriye sürükleyip bırakıp ve bunları birleştirmek suretiyle sağ taraftaki parametreleri girerekten bütün bir sistemi modelliyorsunuz ve sonucunda nasıl bir çıktı alacağınızı öngörmüş oluyorsunuz. Yazılımın temel yetenekleri itiş gücü sistemleri, HVAC, soğutma üniteleri, güç üretimi ve buna benzer dahil olmak üzere enerji dönüştürme sistemlerinde de çalışmanızı tasarlama, modelleme ve keşfetme sürecinde yardımcı olarak karşımıza çıkıyor. Burada bütün bir ekipmanı yani hem diyelim ki bu ekipmanınız hem motordan oluşuyor hem de bir enerji santraliyle birleştirmeniz gereken durumlar da oluşabiliyor. Bu bütün ekipmanları birleştirerekten de bütün genel bir sistemin optimizasyonunu da yine yazılım arayüzü içerisinde sağlayabiliyorsunuz. Bu sayede size hem 0 boyutta hem 1 boyutta sistem modelleme tarafında yazılım yardımcı oluyor. Gerçek dünya koşullarında makine performansınız nasıl çalışacak bunları hem sabit durum için hem geçici durum için yine görüntüleme imkanınızı sağlıyor. İşte özelleştirme yoluyla genişletebildiğiniz ve gömülü sıkıştırılabilir, sıkıştırılamaz akışkanları da girebildiğiniz geniş bir kütüphane de size sunuyor veya da kütüphaneyi manipüle etmenizi de sağlayan bir süreci sağlamış oluyor. Şimdi sözü daha detaylı bir şekilde hem yazılımı hem de yazılım içerisinde yapılmış çeşitli durum çalışmalarını anlatmak üzere Vladislav Bey'e teslim edeceğim. Vladislav, can you hear me?
Yes, I can. Hello,
Okay,
everybody.
very well.
So it's my turn, right? Okay, I will then share my screen. May you please let me know if you can see my screen and hear me as well. Excuse me, Ahmed, may you confirm, please? I'm not sure, just everyone can hear me. Um, so hello. All right. I think in this case I will then just proceed. In case if you will have some questions or some concern, please let me know. So okay, thank you again for introduction, and thank you BS team for having me today here. So everybody for being here, and maybe as first thing I would like to start, I would like to talk about it's that I call here a puzzling challenge. So over here, one of the big hearing thing I keep hearing is that when we are looking at complex system like some aircraft engine is going to be compartmentalized. So of course, when you look at something like this, like a turbofan engine, that's going to be the first thing that comes to mind for most people. That is going to be the system level. But of course, when we start thinking about the system, we're going to also want to start thinking of components. So, and these components, so we may have here fan, we'll have high pressure compressor, low pressure compressor, we'll have turbine, and whenever else you might also have there, if you keep thinking about then was going to have the turbine cooling for the entire cooling system that going from the compressor bleed all the way to the turbine injector. So we are going to have the cooling within blades. Then you can start thinking of lubrication and heat exchangers, or you can start thinking about the fuel supply system. So now that you've got your cycle already set up and you've calculated how much flow of the fuel to provide to the system and how it's going to go from the tank all the way, including the pressure losses we can expect and how you're going to be controlling this and so on. And also things like environmental control system, which we're going to be looking at today. It's an emergency system for oxygen delivery, for example, or of HVAC system for distribution, etc. So as I'm sure you can imagine, when you can start thinking of a complex topic like aircraft engine, all this comes to the mind. And more, but the challenge and really puzzling challenge that we see a lot of this, that since everything is going to be keeply compartmentalized between the different teams or different team members within companies, it becomes quite difficult to ensure that somebody's fan model is going to be well tied in a cycle model, which is going to affect the rotor dynamics and which is going to affect this and that. So really what we are looking for and the main reason behind the new release of software is that we did, and this current webinar is to be able to have as much of the various part of the system that I just talked about to be talking together, not just through some, but the linking of different, not through just but linking different tools, but really go through the merging of most of them. And so it's kind of premise of the webinar and the release we're just going to be discussing. So the software just we can talk about a bit. So it was already mentioned, it's going to be merging and an update of two our legacy tools that we have the cycle software, which was developed for thermodynamic cycle and was mostly a 0D2. And then we have a legacy ExtremeNet tool, which is more of a one-dimensional thermal fluid network software for use in like auxiliary system. And if you want changes, piping or cooling and things of sort, so if you combine the two together, you can get this brand new shiny product, which is really going to be really combining the two and then having some upgrades. I'll be talking about it a bit later. So here, as you can see, the single system, you can look, for example, for propulsion system, and you can look at environmental control system with cycle machine. You're going to be able to also look at the air distribution system, about how really and how the air is going to from the ambient condition all the way through the engine various extractions from the compressor and going through the series of components for cooling, for pressurization, depressurization, for example, the humidity control and things like that, all the way to the place actually where passengers and we personally may be sitting there. So really what we are getting here, it's the best of both worlds, and I've divided this slide vertically, so you just, for those of you who are not too familiar with it, with our cycles, where which one on the left side, and our ExtremeNet software that on the right side. So again, just to kind of give you an idea about some of various capabilities that we are going to be combining and where we're going to see equity discount applications, where we're going to be seeing this kind of systems. Then one major setup of upgrades that we're getting in. That is kind of system that we're going to be in the software itself. And actually, it's all going to be in for steady state and full transient calculations. So you've got plenty of customization opportunities. And of course, you've got this mix and much of different levels of fidelity, 0D versus 1D, in order to, for example, start modeling your system with 0D heat exchanger, and then size who's within the exact system, software, and model. So, okay, the next part of the presentation, if we are going to be talking about environmental control system or ECS, yeah, and pretty much what is going to mean, it's like what we saw in this slide before. Here that actually we are going to be extracting some or bleeding some of air from the compressor so that it can be used as part of your air distribution system to get to your seat. Anytime we are going to be taking air from gas turbine engine, the propulsion of the cycle, that means that the turbine will get less flow rate, that actually will reduce its power production, and that's going to affect the thrust, the efficiency, and things like that, which is exactly what we are going to be talking about as just a very small motion here. So this is pretty well understood concept. So I'm having you more as like a quick reminder that anytime you're going to be again grabbing some air out of compressor or any part of the gas turbine engine, whether it's going to be used for any of whose applications here, ECS, water pressurization system, it's going to be getting pressure for the, let's say, for the bathroom or for the flushing system of the aircraft and things like that, like anti-icing, turbine cooling, engine start, etc. So all of this is effectively going to take somewhere from the engine, and this air, even though it's free, is still going to be costly. And that's going to be in terms of the engine performance, and whose in performances are going to be different as we're going to be looking at different environmental conditions. And that's really one of the things that we are going to be looking at in this presentation, especially in the first case studies. So we are going to look at how kind of costly on performance on the engine bleeding some air from compressor is going to be for different for pretty much altitudes and different phases of flights. So keeping this in mind, it might take sense to start thinking about the system that would be bleedless, meaning that we would not be getting the air from the part of the compressor, but we would be getting it from somewhere else. And that's going to be mostly the topic on the second case study that we're going to see later on. And this is just kind of preview of what we are going to be talking about later. So we'll have just some slides a bit later in order to further describe these case studies I just mentioned. So this slide here is just really a summary of what I just talked about. The environmental control system is really going to be there, and we will see in a few slides to make sure that mostly the cabin conditions where the crew and passengers are going to be sitting are going to be maintained at safe and comfortable levels, and we will see what's going to be pressure, that's going to be humidity, temperature, and things like that. And here we just talk about the fact that the propulsion system is going to suffer or be affected by ambient conditions. So anytime we are going to be changing whose ambient conditions that's happening outside of the aircraft, that's going to affect how the compressor is going to operate. Colder versus hotter flows are going to be leading to different compressor performances. As an example, we'll have a different amount of muscle rate as is going to through the system, and all of this is going to affect the turbine performance. But anything that comes into the compressor is also going to affect anything that's going to be bleeding from it. So if you got different pressure coming into the compressor, you have different pressure and temperature going to the bleed location. That's going to affect your cooling system, which again goes back to turbine performance. And then that's also going to affect anything that's going to be linked to the pneumatic system, including environmental control performance, and all of this ties back into the engine performance. So, and I've just this one slide here, again, just to be a bit more practical with what I just talked about. This is an example of one given gas turbine, and that's just to show you different correction curves based on altitudes, how the pressure is going to be changing based on the temperature, on the flow heat rate, and the output of power of gas turbine engine is going to be changing effective again, and ambient temperature for kind of different data, and also here's effect of humidity. So again, that's just a view in more practical terms that we just talked about in previous slide. Now we're getting into the interesting part. We'll be now well. Hopefully everything so far has been interesting, but we are going to actually start talking about webinar ECS is. So as I mentioned that ECS environmental control system is going to provide a number of different things to the various parts of the engine, mostly to passengers and crew by controlling heating, ventilation, pressurization of the cabin and things like that. But it can also be used to cool avionics because a lot of avionic packages these days, especially in like future applications, are going to be quite heat generating, and therefore the temperature of operation may be above what the acceptable condition for these particular materials and components should really be. So again, this case we could use like ECS to provide acceptable temperature for whose systems. As you can see here, is just a kind of summary of what they're going to be like for various foreseeable conditions that we would imagine from an aircraft. And as you can see, the different pressure for different altitudes, for different humidity, pretty self-explanatory. So, and here on the top, we can see the typical comfort conditions that would see on aircraft. And here the humidity is actually mostly going to be dependent on the duration of your flight. So for ECS, we are going to see a number of different technologies. The convective kinds are going to be one of the most common. And in this case, what we do is we operate an open loop system where air is going to be a refrigerant or the working through. So we have a bleed air from the engine that is going to be conditioned and fed into the aircraft for passengers in the air. On this, so furthermore, this kind of categorization is going to be separated to two different categories. And we are going to have low pressure, what we call water separation system, and the high pressure here on this side. So the difference is really going to be in the water extraction loop, and as the name implies, in the low pressure we are going to have the fewer components. That's typically going to result in a lower weight for the entire system. But with this kind of system, sometimes happens that you're going to have some water, like water droplet formation, that will not necessarily be easy to get rid of, and that can be provide some. It can lead to some icing in part of the system, which is going to be detrimental to the integrity of the system as well as its performance. So that's why this kind of system is going to be a bit more interesting. Excuse me. So if we take a look at one of whose example, I just want to show you here that we have the bleed air coming from the engine. This is going to pass through the heat exchanger, a compressor, a second heat exchanger, turbine, etc. So then we are going to take this into cabin. And as I mentioned, the refrigerant here or the cooling fluid we are going to be using is going to be the RAM air, which is going to be through these two heat exchangers, and then going to be to have a fan that's will exhaust this back to the atmosphere. So on the other side, we also have the electrical ECS, and that's going to be one of the focus of what we will be talking about. In this case, we are completely separating where where the ECS and the engine are going to operate, and there is actually no connection between two components. So that's really going to be the case of bleedless system that we are going to be talking about, where we are not effectively taking air from the engine, but we are going to be taking it just from anywhere else. So for this, again, we are going to have some RAM air that's going to get compressed, and that's going to be powered not by gas turbine engine anymore. That's going to be powered with some electromotor, which is why it's called actually electrical ECS. And then the rest is going to be pretty similar. So same concept here for cycle machine. And the only difference is that now the pressurization is going to be done using some electromotor driven compressors instead of portion of the gas turbine engine compressor. And finally, a third kind that we can see is going to be, for example, some kind of vapor compression cycle. This is not super widely spread in terms of application. It's going to be mostly used in helicopter. We are not going to dive deeper into this particular kind of configuration, but you can see what that would look like as schematic here. In case you're interested, I figure out that this would be valuable information for you as well. In summary of this section, not for the entire webinar, we've seen that the ECS energy can be taken from different sources. It can be taken from compressor bleed ports and exhaust from the gas turbine engine. That means that we are going to reduce effectively the engine power, or we can compensate the meaning bringing up the power simply by adding more fuel, which is going to mean having more fuel on board. So more mass, of course, and of course more cost. For the fuel as well. And the signal option here that we're considering, it's going to be take this ECS energy from some electrical source, which can be stored in batteries or fuel cells simply generated by motors. So we'll talk about what is ECS is and really what is going to be doing into the flight kind of parameters. It's going to be controlling. We talk about how the air extraction is going to be influencing the thrust. Yes, so I think the point got across for this, and really what the main challenge then becomes is going to be for us effectively estimate the extraction muscle rate and the condition, meaning also, for example, the location of where we are going to be doing the extraction from the compressor bleed for different regimes, meaning different altitudes, different grooves versus takeoff, and things like that. So as we want this estimation of mass flow or condition to be accurate as possible so that we can design our engine in the entire system effectively, and we can also operate it as optimum specific fuel consumption. Sorry. So that's what we're going to see here with specific fuel consumption. So the solution that we came up with is to have a fully integrated system that's going to model components in the entire system within a single tool. And hopefully you have been waking up here as I'm going with this. So, okay, let's take a look at the two case studies that that we prepared for this webinar. The first one is going to be looking at the integration of ECS and aircraft engine. For this, we are looking at mid-roll aircraft. We based on all of our data on the A320 aircraft, but it can also be, of course, applied to any system. And we did not poorly stick to the data that was in there, just kind of use it as modified base value if you want. So what we are going to be interested in this particular first case is going to determine the amount of bleed air and its condition so that we can get acceptable condition, the cabin and the cargo from the environmental control system. And for the second thing we are going to be looking at, it's how the bleed amount and condition is going to be affecting the performance of the engine, including the thrust, specific fuel consumption, etc. So pretty much we are looking at ECS outlet, meaning the cabin and cargo conditions, and we are also looking at the engine performance. And the second case study is going to be a comparison of the breathe air system, meaning the first case study pretty much of electrical ECS that we are going to be shortening as ECS throughout the entire mission. And for this, we are going to be looking at the comparison of the turbine engine fuel consumption, which we know is going to be higher for the case of breathless air, but also the overall energy usage throughout the entire system, so the propulsion and then the ECS. All right, so for the first case study, again based on the integration of the engine and the auxiliary system, which is the case study is the ECS, we are going to be looking at various flight conditions in order to determine what would lead to comfortable conditions inside the cabin. And that's going to allow us to get more information on the thrust, fuel consumption, overall engine efficiency, energy losses due to piping friction, since we are going to be able to model the entire air distribution system using 1D components, or thermodynamic losses. Same thing, because here again thermal fluid networks will be able to look at hydraulic and thermal losses, looking at various conditions inside the cabin, looking at different thermal load ranges, including the humidity. So in terms of design requirements, this is typically what the cabin conditions should be. So you can see it's more or less around 22 Celsius degree. So, excuse me. So the pressure needs to be above 75 kilopascal. And also we need to make sure that we vary this pressure inside the cabin fairly and gently, so we don't have anybody pass out, and be in pain, which is not funny either when you are on the aircraft. And of course, the humidity is going to be a parameter that's going to be controlled again, just to make sure that the cabin and crew is going to the cabin passengers are going to be comfortable. And then when we look at the typical environmental control system with bleed air, technically that is traditionally used, you can see that the pressure and temperature it is getting from the engine is going to be about 3 to 4 times what the pressure should be. And you can see here the temperature is going to be quite high. So therefore that's going to require some expansion of the fluid and also some cooling to be able to put it into the cabin. So here we can see this graph, how the cabin pressure is typically going to be controlled, as well as how the outside air pressure is going to be changing for different altitudes. Okay, so we've just talked about the fact that we have a system and we now we need to design it. But how actually we're going to model the performance of various components? So for this, there is a kind of three different approaches. There is a kind of traditional approach, or there is a digital engineering approach in the center, or there is a, I would say, futuristic, but still realistic approach. So it gives you whenever you you want to use, but we are typically used it for cycle level, especially when you're doing case studies and things like this is going to be used for reference map for various components. However, one of the things that we really find is as you're going to be bleeding some air from the compressor, you might deviate some a little bit from the performance, so it doesn't become as accurate as you want to be. Maybe it's fine for a high-level study, but if you're going to be refining your final design, it's probably a good idea to kind of step away from this kind of things, unless you're already accounting for the correct bleed conditions from the compressor in order to determine whose maps. The second approach is, which I've kindly nicknamed, the digital engineering one, is going to be using a more kind of high fidelity code that could be 1D, 2D, or 3-dimensional. or whatever you want, probably one of whose or even some 0D models are to be pretty accurate for. But here's just an example. And here I'm showing you results of 2D calculation that was done in our Extreme software, so that you can actually link that particular component as part of your cycle, as you are going to be looking at optimizations and of design conditions for the system. You don't have to rely on approximations of the map where you can actually calculate the reference of this component for conditions that which is going to be operating, and what I adopt as a realistic but futuristic method is going to be some artificial intelligence or machine learning in order to be able to predict what the performance map would be based on some training data. That's kind of summaries the two here and put in the brain behind it. So eventually this kind of system will come, it's going to be something like where we have inside of one system, the engine, we are going to have the ECS, and then they're going to have the thermal fluid network, which is going to provide the distribution to the cabin. And we'll talk about this already. I already introduced it. So now if we start looking at the results, it's quite a little bit on the graph here, but I want to walk you through just what the graphs are going to look like and what we actually did before. I got into the results. So here is the first, we are looking at the engine performance for the number of different what we call flight points or flight conditions through a given mission. Here we are looking at from takeoff condition, which is going to be in gray box, to the climb, which is going to be in red boxes, and finally the cruise conditions, which are going to be in the green one. And so we can see here the flight points, which are not uniformly distributed, of course, but you can see here the various altitudes and condition that we are looking. So actually this flight condition correspond for cruise mode correspond to about 30,000 feet, which is typical altitude for cruise for the engine. Well, and here you can see that you've got two different zeros and two different 50s. For example, one with and one without star. Here is simply referred to offset temperature that we can actually, for which we can adjust the ambient conditions, and that's going to affect how the system is going to be operating. So here, for example, we can see there can be a little bit of a difference, also kind of hard to see on this graph between whose 2 points. And this graph here, as you can see, already shows the thrust of the engine. It's going to be the thrust specific fuel consumption. So specific fuel consumption divided by amount of thrust it's producing. And here we can see the result of how much bleed air we actually get in from the engine in order to provide the cabin conditions, which are going to be shown in the next slide. So now we are looking at the ECS outlet parameters. So what is coming into the cabin all the way from the ambient air through the engine, through the cycle machine and air distribution system. So here you can see the same flight points that are presented on the slide. And you can see that in this case, how the cabin pressure is going to be maintained above this limit here, and how the cabin temperature is going to be maintained between 2 points or 2 limits, and how the relative humidity can be controlled to be whatever or whatever value you want. So you can see it's around the percent for the cruise conditions, going to be a little bit lower for this case, and you can also see how the air velocity is going to be changing again for different phases of flight. So the reason why these graphs are going to be a little bit not so smooth, I would say, is because here we're actually using the given logic that we implemented ourselves, but that's going to be purely up to user in order to control how much air we are going to take. So that's going to be through some opening and closing the valves, how much accumulation within the cabinet we want to do, and how much relative humidity we want to control, and things like that. So these graphs are not meant to be. That's what your engine should output, or that's your ECS should output. It's really more to show you that you can actually use different control strategies and logics in order to make sure that you're going to get the results that you would need based on the requirements. So that you have for your engine, or what you think might be the optimum for. So in summary, for this case study here, we look at the entire propulsion and ESS in order to optimize the cabinet commissions, so wherever we want, and then we could also have some logic in there, for example, to still maintain all of these requirements while increasing the performance of the engine. So for the second case study, we are now going to be looking at different technologies. So if you recall, we're going to be comparing the traditional ECS system that we just used, just saw in case study. Number one, we are taking some bleed air from compressor, and then we are going to be comparing this to the electrical ECS. Okay, so comparison is going to be done for the same cabin conditions, just so we are kind of comparing as like apple to apple as possible. The ECS bleed air is typically going to split into one air ACM or air cycle machine per engine. The particular aircraft we are looking at is going to have two different engines, and the size of this air cycle machine is going to dictate the various ventilation requirements. So that's going to be how much air each passenger at minimum needs to be getting from the variable. So that you can see, it's about 6 grams per second per passenger, and if you are considering A320, which has 200 passengers, that gives us 1.2 kilograms per second minimum of flow rate that's going through the ventilation system. And that's again going to be for both engines we are going to be considering. And this one, so we're going to be looking at a minimum of 0.6 for this part growth today. And we could have considered both here. So we just decided to look at a typical value. It's going to be around 2 kilograms per second for the entire aircraft. And one of the things that we are going to discuss here, since one of the objectives is going to be for us to look at overall energy consumption of the system, we have to come up with a definition of what the compressor work is going to be for the bleed air system. So pretty much here that we are doing a simple equation. We were looking at the ambient conditions and the temperature at the bleed location and how much mass flow we've got to be extracting. So this is the way we're estimating what the compressor work is for the particular smaller flow rate between the inlet and whatever location we are going to be extracting the flow out, and that comes to about 200 kilowatt per pack. And this is, you can read if you want, but I'll look at it a bit later. So this is more kind of reminders of what we talked about in the previous slides. This is exactly the same model that we look at this case study number one, and the only thing you want to bring your attention here is what the pressure is coming out of some kind out of engine. So at this location here, we are going to be, so you can see the pressure of 240 kilopascal versus 75. That's going to be minimum. And we don't want to blasting people in the face with this, especially hot air as they're going to be here. So here we can see actually the temperature against what to need to be to, and significantly cold. So just get of the summary and with the highlight of whose two figures here. So if we look at the electrical ECS, that's going to be obviously to be different system, because now we are looking at a complete disconnect between the gas turbine engine and the ECS, which can be done within the same model. So it's just the two are not connected anymore, and there is no flow from here, like from the GT engine to the environmental control system. And we are not showing on here, but if you were to go on the right side out of the screen, that would have the same distribution system. And here you can see that when you're using RAM air from the electrical compressor, that's going to get you to pressure and temperature. It's going to be a lot closer than when you would have its like bleed air condition. And that's because you really can design whole systems so they can provide as close as possible conditions, so that you don't have to depressurize the system and cool it too much afterwards. And here I just wanted to show an example of ECS integration on the Boeing 777 aircraft, which is so you were taking some of the flow and heat from outside. So here we are going to here are going to be the results. So again, we are going to be looking at the engine performance for the first case, and then we are going to be looking at the outlet parameters. So here we are actually comparing the two technologies together. So we are looking at the specific fuel consumption normalized based on the thrust for different flight points. So same as before, and here if you look at the blue diamonds and the blue curve, is going to be the case study one previous, and the traditional approach of using bleed air in order to use the ESS, and the yellow-orange line with orange and the blue diamonds is going to be bleedless technology, which doesn't have bleed, obviously. And it's going to be powered by electrical ECS, and we can see in this case very clearly that as we are going to go from one to another, there is going to be difference in a specific fuel consumption, as we would imagine the fuel consumption is going to be higher in case of the media system. Just like what we had anticipated earlier, and these numbers here, the difference are going to be shown in the graph right here, and that's just kind of give you an idea in terms of percentages. That will be anywhere from about 2% to about 6% difference in the fuel consumption. And here what we can see also is a most of the difference is going to be at cruise condition. And there is going to be some difference to the climb, and then for the takeoff, it doesn't really have much difference, because we don't really need to turn on the ECS on whose altitudes. And here actually you can see that the pretty much value of mass flow rate is going to be extracted, which is about 1 kilogram per second, which is going to be these values right here in the particular graph, so you have the same kind of information. And you can see here the 6% we are talking about for the cruise condition, but here we are looking at a different amount of bleed air, so you can see as you would require some more bleed from the engine, that fuel can be skyrocket. And here's the flight point again, just to show you what altitudes are each of these conditions going to be taken as. So, okay, in terms of ECS parameters here, again, we looked at a different amount of flow rates. I'm going to be running like a shortened time here, so I will try to make it quick, but pretty much I see like 403. So supply air flow rates, we are able to get the desired cabin pressure using whatever logic we implemented in here. Something for the cabin temperature, or for the humidity and for the velocity. So you can see if we were to put a kind of maximum value on the air velocities, if we wanted to then allow us to see actually one of the sizings is going to be is not perfectly suited for the given application. But what I want to draw your attention here is going to be the power against for whose different air supply flow rates. And if we look at if we are looking at the cases, so we were about at 200 kilowatt for the power, and if you are looking at the same conditions and the curves for electrical ECS, we are going to be looking at around 125 kilowatt of power. So that makes quite a big difference in the overall energy usage on the aircraft. And here again we talk about the temperature and the pressure that can be actually quite different too. So now I will, as I have probably quite a limited time, I would like to do some very short software demonstration of extreme system simulation where actually the case study were performed. And so now you can see actually the general interface of extreme system simulation. So usually we have all the library and all the component on the left side that allow us to have all components in one place, and using these components we can build any kind of systems that you may be interested in related to aerospace or some heat pump or some power generation system and so on. And the logic actually is quite simple, so we just need to add some component like compressor. In the compressor on the right side we have all the properties related to the component, so we can put here and estimate which parameters may be our boundary conditions in the red color. Besides this we have also basic performance of the parameter, and actually we can specify our boundary conditions or red parameters in different ways, like by just single constant value or using some scripting, or actually using scripting we can put some our formulas, equations, or functions in order to estimate the parameter, yes. And or using table where we actually you can use some interpolation, extrapolation methods based on the table we import in here. So, and actually then once we set up our model, we can just expand our system, connecting it in the same way, and in this way expand our system until it's got completed, so and so on. And for another example that actually we consider today, so here is already more complicated system. Yes, so we have here the electrical environmental control system that includes here the ambient, and as I mentioned earlier, so we can specify here the ambient conditions according to EISA standards. Yes, so we can also put here the offset temperature and pressure, considering different scenarios like weather, etc. So this air will actually flow through the intakes that actually may go to the compressor with electromotor side. Then it will flow through the one heat exchanger, then through the compressor to another heat exchanger, then through turbine. And this pressure and temperature may be controlled also by side valve, let's say. And for cooling side, the air may be coming from this another intake, yet through both heat exchanger and then blow out by the fan. And actually after our passing air cycling machine here, the air will go through the air distribution system, where actually directly to the passengers, to the crew, and so on. And from another side, so here we already have a more traditional bleed air system. So here we already more complex aircraft engine that actually has some boundary conditions from the ambient point, and this logic is the same. So air passing the intakes, the fan, the low pressure compressor, high pressure compressor. some air is then extracted from the high pressure stages, and then it going through the going to the environmental control system, and actually here having all the operations like for the control system, using some valves, like throttle valves that may help us to regulate the pressure and temperature at the outside of the air cycling machine, and also some control for humidity level. So we'll have here humidifier and the water separation element. And after that, as already mentioned, yes, so it will flow to the more detailed one-dimensional thermal fluid network system that actually is our air distribution system. So, and here already more take into account more complex factors like geometries, gravities, or swirling if we are considering some rotating system. We can estimate the heat losses, pressure losses, and at the end get the required cabin conditions that actually we are looking for. And also besides this, actually, yes, we can consider different case studies, scenarios, whether we want to design our system or we want to perform analysis of it. And if we look at the compressor, for example, it's possible to upload some performance maps that actually may be designed from somewhere else, yeah, and use this performance map that will be based typically on any of your dependencies or the default ones, yes, in order to estimate the pressure ratio and efficiency of the turbo machines. So actually that's all from my side for today. Thank you very much for listening and for attending the webinar. So that's all from my side. Thank you.
Thank you very much, Vladislav, for your presentation and contribution. I had a connection problem at the beginning of the webinar. So sorry, everyone. We don't have any question. I think there's a very clear and beautiful explanation for your presentation. And I closed webinar in Turkish, Vladislav. Thank you again. Herkese teşekkür ederiz katılımınız için. Konumuz environment control sistem üzerineydi ama bir boyutlu tarafta webinarın başında da belirttiğim gibi çok detaylı sistemleri inceleyebiliyorsunuz. Çok yüksek sayıda sistemi inceleyebiliyorsunuz. Bu sistemlerden veya da benzeri bir boyutlu olarak çalışmak istediğiniz sistemler olduğu takdirde her zaman için çekinmeden bizlere ulaşabilirsiniz. Gerek yüz yüze gerek online toplantılarla problemi çözmeye çalışırız. Katılımınız için tekrardan teşekkür ederiz. Herkese iyi günler dilerim. Have a nice day everyone. Bye bye.